This is B. Naresh, working as the assistant professor in IEC department. And today's topic is transistor biasing and stabilization. So, why this biasing is required and what is the need of stabilization? And we know that the transistor means here we are going to use a bipolar junction transistor. So, in this bipolar junction transistor, we have the two types of the transistors. One is NPN transistor, another one is PNP transistor. The major application of this transistor is amplifier. Then, if you want to act as an amplifier, means the transistor is acts as an amplifier, we need to make that biasing condition, means the input junction is forward bias and output junction is reverse bias. Means we need to maintain a proper DC biasing to produce the faithful amplification of a transistor or for amplifier circuit. We require the biasing concepts. So that is the reason for an amplifier circuit to produce the distortion free output. So we require the some supply voltages, means how much DC voltages are required input side as well as the output side, along with the bias resistances. So based on these biasing voltages and the resistances, we need to maintain a proper operating point or a Q point in the active region. So means when we can say that the transistor is an active region, means based on the configurations, we have the transistor have two junctions. One junction is emitter base junction, another junction is collector base junction. If emitter base junction is forward bias, collector base junction is a reverse bias, then we can say that the mode of region is active region. So hence in active region only the transistor is acts as a amplifier. Then in that also we need to maintain at which particular point the transistor is acts as a perfect amplifier. For this case, we need to define a proper operating point that can be done through these biasing conditions. So hence the voltages, what are the voltages and the currents are called the quotient values, which determines the Q point for the transistor. So that is the reason. The process of this giving proper supply voltages as well as resistances to obtain the proper Q point is called as the biasing. Now in that case, now we are going to discuss. So let us consider a common emitter configuration. So here I use a NPN transistor. Let us take this is collector, base and emitter. And for this case, I use that common emitter configuration. So means, and the base is acts as a input, collector is acts as a output. And the type of the transistor is NPN transistor, means the collector terminal is N, base terminal is a P, and emitter terminal is L. And now first we need to decide the transistor should be in the active region. So means input junction should be forward bias and output junction should be reverse bias. So here the input junction is base along with the emitter. Now base is made with P-type material. Hence we know that to make the forward bias, let us take if a normal PN junction diode. This is P and N. When a P is biased with the positive pole of the battery with respect to the cathode, then we can say that that particular PN junction diode is acts as a forward bias. That is the reason. And here the base is made up with P-type material, hence it is a biased through the positive pole of the battery, and that biasing voltage here it is represented as a VBB. Hence that emitter base junction is, and now it is acts as a forward bias. Similarly, we need to maintain output junction should be reverse bias. And here the output is taken across the collector. The collector is made up with N-type material. Hence, N is, so how you can say that the particular PN is reverse bias means, again this P-type material N-type. P is connected with the negative pole of the battery and the positive pole of the battery is connected with the N-type material. Then we can say that this is reverse bias. Hence, the collector is made up with the N-type material. Hence, this N is biased with the positive pole of the battery with respect to the emitter. Hence, Now this output junction is acts as a reverse bias. Through the some biasing resistances across the output side, the biasing resistance is represented as collector resistance. Across the input side, the biasing resistance is represented as a base resistance. So this way of approaching the voltages and the currents along with the proper resistances to maintain or to produce the distortion free operate or to maintain a proper Q point is nothing but a biasing or a transistor biasing. So from this, now we need to determine the a proper Q point. So how we are going to identify the a proper Q point? To determine this proper Q point, we need to identify the two analyses here, a DC analysis as well as the AC analysis. Means we need to take DC load line analysis and AC load line analysis. And here this is represented as a VBE, the potential difference between base and the emitter. And similarly, the voltage between collector and emitter, that is represented as VCE. Now, to identify this a proper Q point, now we are going to examine the two load line analysis here. One is the DC load line analysis, another one is the AC load line analysis. First, we'll see the DC load line. Means in the absence of AC signal, means we need to remove the AC input signal. Then we need to identify what is the DC equivalent circuit. So hence from the given circuit, so if you observe the circuit, now I'm going to find out means the Q point is always the operating point or a Q point. The operating point is also called the Q point. The Q point is a functioning of your collector current and output voltage. In this case, the output voltage is represented as VCE and output current is represented as IC. So hence, in general, the operating point is a functioning of the output current and output voltage. From this given circuit, the output current is represented as collector current and output voltage is represented as VC. So hence, now we need to identify the Q point for collector current and the Q point for the output voltage. To determine this Q point, now we need to apply a KVL analysis at the output side. That is the reason. So if you are writing like this, means how to write this one? The VCC is equal means then the voltage drop across the collector resistance along with the potential difference between collector and emitter voltage, that is equal to VCC. Hence, we can write this VCC is equal to, so the voltage drop across the, so hence VCC is equal to the voltage drop across the collector resistance and the voltage drop across the collector to emitter. Means the voltage drop across the collector resistance is represented as I into RC, means IC into RC plus the voltage drop between collector to emitter, that is represented as VC. Hence, that is the reason. From that circuit or from the output loop, we represent it as VCC is equal to IC times of RC plus VC. From this, I am going to identify the output voltage. What is the output voltage? The output voltage is VCE. Hence, we need to determine the VCE from this circuit. So, what is the VCE parameter? VCE is equal to VCC minus IC into RC. Hence, so from this above equation, I derive this. The VCE is equal to VCC minus IC times of RC. Now, we need to locate from the transistor characteristics. We need to identify the DC load line. To observe this DC load line, so here I am going to assume if from this given equation, if the collector current is a 0, means I am making this one VCG is equal to VCC minus IC times of RC. Here I assume that the collector current is a 0. So then VCE equal to VCC minus 0 into RC. That becomes, what happens? VCE is equal to VCC. So that is the reason. At when the potential difference between collector and emitter voltage is equal to VCC point. The collector current is represented as 0, or if the collector current is a 0, the voltage across the collector to emitter voltage is equal to your VCC point. Similarly, let us consider if the VCC is a 0, if the VCE is a 0, so means in the given relation, if a VCE is a 0, that is 0 equal to VCC minus IC times of RC. Hence, VCC is equal to IC into RC. Then we need to find out what is the maximum collector current when the VCE is a 0, hence IC maximum is represented as VCC by RC. So these are the two coordinates we observed at the minimum collector current and minimum output voltage. At minimum collector current, the output voltage is approximately equal to VCC. Why? Because of that. So the current is not flowing in a output side. The output junction is the reverse bias. So we know that under the reverse bias, the the output voltage across the diode is approximately equal to given input voltage. So hence, here also it satisfies the same relation. When the minimum current is flowing through the network, the output voltage is approximately equal to given input voltage, that is VCC. And similarly, when the VCE minimum voltage is passing through circuit, the collector current is the maximum, that is VCC by RC. So to draw the DC load line, now first we need to draw the coordinates in a output circuit. Hence, let us consider this is a VCE and I consider the output parameter, output collector current and output voltage. Then we need to draw the coordinates when VCE equal to 0, when a VCE equal to 0, then the collector current is represented as VCC by RC. So hence, at this point, if a VCE is a 0, let us take, I assume this VCE is a 0. At which VCE is a 0, we observe that we have the two parameters. When VCE is a 0, the collector current is represented as VCC by RC. If the collector current is a 0, we observe that VCE is approximately equal to VCC. Let us consider if a VCE is a 0 and at this point the collector current is a maximum, this node is represented as VCC by RC. Similarly, when IC is a 0, means this is the collector current, IC is a 0, that indicates that VC is equal to VCC, means the maximum reverse voltage, that is VCC. Now you can then join these two coordinates that indicates the DC load. And then how we are going to take the Q point. The Q point is always the center of the DC load line. Hence, we represented the center of the DC load line, Q point. So means from this, so ICQ is represented as, means half of the IC value, and the VCEQ is also represented as half of the VCE value. Hence, the Q point is represented as VCC by 2 times RC, and this is VCC by 2. That is the reason. This is VCEQ. VC is equal to half of the VCC. ICEQ is equal to half of the IC maximum, that is VCC by RC. And then this intersecting point in an active region and the center of the DC load line indicates the Q point. Now we'll see what happens if a Q point is suppose if a Q point is shifted to saturation region. So if the Q point is shifted to saturation region, so then it loses some amount of the given signal. And similar to that, if a Q point is located nearer to the cutoff point, so means now the Q point I'm shifting towards the near the cutoff point, then also it loses the some amount of given input signal. That is the reason we observe the Q point is always located in center of the DC load line without losing any information of a given signal. So that is the reason to produce a faithful amplification. So we need to maintain the operating point is always the center of the DC load line, and there should be an active region. Now, what is the importance of AC load line? So up to this point, we observed that in the absence of AC source, we identified the Q point under the DC biasing condition. Now we'll see the AC load line analysis. Means now we are going to apply a AC signal. So to determine this AC load line, now first we need to draw the DC load line. Then we need to locate the Q point. After that, we need to apply the amount of AC signal or passing through the given circuit. Then we need to identify the AC load line. At this point, so here the AC load line is also passing through this DC operating point or the Q point. So hence, let us consider for the same circuit. So now I'm going to passing through the given AC signal to the CE amplifier circuit. So now this is a Vin is passing through input of the transistor. Then let's take this the base, again emitter and a collector. The type of the transistor is NPN. Then we know that to make the amplifier, then the transistor should be in an active region. So means if you want to make this active region, the emitter base junction should be, or input junction should be forward bias. Hence, so this is the base is made up with a P-type material, and P is connected to with internally already we made that one. Then similar to that, the output junction we need to make the reverse bias, and collector is made up with N-type, and it is connected with a plus VCC. Then now we are going to apply the AC signal. So whenever you are passing the DC signal, the capacitor blocks the DC component, hence it acts as the open circuit. Then that is the reason under the DC condition, the input is AC series is not passing through this input of the transistor. Under this condition, now we need to identify how to identify the AC load line, then how to determine the Q point with respect to this given input signal. So for this case, let us consider the given equivalent circuit is converted into, this is we know the DC equivalent circuit. So means the DC equivalent circuit is observed under the absence of given AC source. Means, so if there is no AC source, means the capacitor blocks the DC component, hence this RB directly is connected to this voltage source here, DC voltage source, and RC is also passing through the DC voltage source. So hence, so this input side is again connected to plus positive pole of the battery, and collector is also connected to positive pole of the battery. Then your input junction becomes forward bias, and output junction becomes reverse bias. Similar to that, if you want to calculate the AC load line, and then so under this condition, what happened under this AC load condition, and the capacitor, these two capacitors are acts as a means CV and CC are acts as a short circuit. So means if it is a short circuit, means AC signal is passing through this biasing resistance towards the base terminal of the transistor. That is the reason the given input signal is passing through biasing resistance towards the base of the terminal. And if you observe the output side, under this AC analysis, means we know that the capacitor acts as a short circuit. If this CC coupling capacitor is acts as a short circuit, means this collector resistance and the load resistance are becomes parallel, and that is the reason I represented as RC and RL. Both these two resistances are under the parallel combination. Now we need to calculate how much maximum collector current and how much maximum VCE voltage will be generated with respect to this load line analysis. Now I'm going to calculate the maximum VCE, means so under this AC condition. So it is represented as, so where again I taken as this, if you observe this one in this condition, and here we have some two resistances. These two resistances are parallel combination. That is the reason I'm going to find out the equivalent resistance. That equivalent resistance here is represented as RAC. And this RAC is a parallel combination with collector resistance and load resistance. Hence, this AC resistance is represented as RC into RL by RC plus RL. Now, and we know that this AC load line is also passing through the Q point. So that is the reason. While calculating this maximum AC voltage, maximum collector current and a maximum output voltage, we need to consider that Q point also. So hence from that, here I represented as the maximum VCE, means it is passing through that Q point. What is the Q point on the DC load line? We observed that it is the functioning of IC and VCE. Hence, we identified ICQ as well as the VCEQ. So here we identify the VCE and it is passing through the Q point along with V means, again we need to write V is equal to I into R. I means your ICQ and R means your I is represented as ICQ, Q point. R here, under the AC equivalent circuit, the equivalent resistance is R is represented as RAC. So hence the VCE, the maximum VCE is represented as VCEQ plus ICQ into RAC. And similarly, if you want to calculate the maximum IC, so means this maximum collector current is also passing through the Q point collector current, that is represented as ICQ. Again, we know that I means is the ratio of voltage to the resistance. So here the voltage means VCEQ, but R means RAC. Hence, now we are going to plot these two parameters in load line analysis concepts. Hence, let us consider here. So the B point here, it is represented. This point is represented as a VCC, and this point when VCE is a 0 under the DC condition, when VCE is a 0, the maximum collector current is represented as VCC by RC. Similarly, when IC is a 0, the maximum VC is represented as VCC. This intersecting of A and B is nothing but your DC load line. Clear? And similarly, now we observed that the AC load line parameters maximum IC and the maximum VCE. Hence, this point maximum IC is what is the representation ICQ plus VCQ by RC. That is a shift towards this amount along with collector current and along some current is also increases. So this is also I. So I1 plus along with this collector current, hence current parameters increases. Then similarly, we also observe that here this point VCEQ plus IC into RC, and this shift to be below this line. And this intersecting of C and D is passing through the Q point. That line here is called as the DC. So this line here is called as the AC load line. And here this is the intersecting of means the center of the DC load line is nothing but your VCEQ as well as your ICQ. That point indicates the Q point. So this Q point, we are going to make that. So this based on this operating point, we are providing the faithful amplification for using the transistor. Now, so up to this point, we observed that how we are going to make the biasing to produce a faithful amplification by using the amplifier circuits. So even though we are now the next aims we need to maintain that operating point is stable. Means why? Because of that we have the transistor. The transistor parameters are so temperature as per the semiconductor principle. For every 10 degrees centigrade, the reverse saturation current becomes double. So that is the reason. If you observe the diode current expression, I is equal to I naught into e power V by eta times of Vt minus 1. So here where the I naught is a reverse saturation current. So hence for every 10 degree centigrade, the reverse saturation current becomes double. So that is the reason. So these parameters due to the temperature, the collector current is the changes. So if collector current is the changes, automatically the Q point is also changes. But our aim to be, we need to maintain irrespective of the temperature dependent parameter, we need to maintain a Q point is stable. That condition is nothing but a stabilization. So here the stabilization, why the stabilizations are required because due to this region. So the temperature depends upon the current. Means if the temperature is the changes, your reverse saturation current is the changes, hence IC is also changing. Why? Because of that we know that IC is equal to beta times of IB plus 1 plus beta times of IC naught. So here the temperature is the changes, the reverse saturation current is the changes, means IC naught is the changes. If IC naught is the changes, the collector current is also changes. So that is the one parameter. And second one, individual variations, means transistor to transistor parameter. Then other one is thermal due to that heat. So that is all these parameters we need to maintain a proper Q point to maintain the or to produce a faithful amplification. This stabilization is required. So how to find out the stabilization techniques? So means these techniques consist of a biasing circuit and which permits the variation of the base current IB. Means so we know that IC is equal to beta times IB plus 1 plus beta times of IC. So here what we just know, if IC naught is the changes, IC the changes. So that's the reason. To compensate this change in collector current, we need to compensate through this base current. So if base current is reduces, then automatically that collector current is also reduces. Hence, the compensation is hence the Q point becomes your stable. So that is the reason. To maintain this proper collector current, so we need to variation with respect to your reverse saturation current and beat. So how this collector current changes means reverse saturation current. So one is reverse saturation current, one is with respect to your DC current again, that is a beta, and one is with respect to the VBE parameters also, means the potential difference between a base and emitter. Means if a VBE means if a VBE is a changes, IB is a changes. If IB is also changes, then IC is also changes. This is the second parameter. The first parameter, temperature is changes. Your IC node is changes. If IC node is changes, IC is also changes. Again, from this mathematical relation, if IC is equal to beta times of IB, from this mathematical relation, if a beta is changes also, the collector current is a change. So irrespective of any parameter, if any parameter is affected, the collector current is the changes. So hence, the Q point is also changes. If a Q point is the changes and there is no faithful amplification in a transistor amplifier, so that is the reason. Irrespective of all these parameters, we need to maintain a proper Q point to stimulate or to produce the faithful amplifications in a transistor amplifier. So that can be observed with respect to these three parameters here, the stability factor. With the variation of these three, what the three parameters we observed? IC naught, beta, and a VBE. So hence we need to maintain S stabilize. So here we have the three factors S, S dash, and S double dash. So here the S is defined as the rate of change of collector current with respect to the reverse saturation current, means how this collector current is changes with respect to the your reverse saturation current. So that should be observed in terms of your S. And at this point, the remaining two parameters beta and VB be taken as a constant. And similarly, S dash. So this S dash parameter is observed how this collector current is changes with respect to the change in base to emitter voltage. So that is the reason. S dash is defined as it is the rate of change of collector current with respect to VBE by maintaining this beta and IC naught is a constant. The third parameter is, in this case, we are going to observe how this collector current changes with respect to the change in current gain or a DC current gain. So that is the reason S double dash is defined as the rate of change of collector current with respect to the rate of change of DC current gain. And at this condition, we are maintaining this VBE and reverse saturation current circle. So by using these three parameters, we are adding the stability factor. So S, S dash, and S double dash. On all these cases, we are identifying that how this collector current changes with respect to the change in reverse saturation current or the change in base to emitter voltage or with respect to the change in DC current again. Along this, we need to maintain a proper stabilization techniques to maintain a proper Q point to produce the faithful amplification. So, and up to this point, today we discussed that a transistor biasing, how we are going to make the biasing, and how to maintain the stabilization with respect to the temperature dependence parameters. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.